Welcome to our webinar, Eco-Retrofit for Householders, Understanding Retrofit. I'm really pleased to have Marion Lloyd Jones of People Powered Retrofit and Carbon Co-op here today to speak to us. So for tonight's agenda, I'm going to spend just a couple of minutes with an introduction, then it'll be over to Marion to talk about Eco-Retrofit for householders. Then we'll have about 30 minutes for Q&A and a poll and just cover some next events and so on afterwards. So without further ado, I expect many of you have come across Cumbria Action for Sustainability, and anyone who's come to a previous webinar will have seen this slide and probably heard me talking about it. So I'm not going to repeat all of that now, but I do encourage you, if you're not familiar with the whole wide range of things that CAS does, please go on our website, please have a look around, and please get an idea of the kind of things that we're doing, because it's not just all about retrofit, there's so much else that we're doing as well. Within the energy team, we actually have several different projects going on. We've got free help we can give to people like Cold to Cozy Homes, Cumbria, free short general advice calls if people ring us up with a specific question, and free 30-minute retrofit consultation by phone for those people who would like to know how to get started perhaps. We also run paid for services, so we have our energy audits, the Home Retrofit Planner, which is an in-depth energy audit to create a whole house plan. We can do thermal imaging in the winter, and we offer other energy advice. And of course, we do courses and webinars like this one. Sometimes they're free, sometimes they're paid for. We're really fortunate that with these courses, they're funded by Energy Redress. But for those of you who've already made a donation towards the cost of this webinar, we're a really big thank you, because it really does help us do more and make our webinars and our other activities go further. So for the first poll, just like to get an understanding of your current level of knowledge about retrofit. So I don't know if my colleague will be able to kick off the poll. Rob, if you're able to kick off the poll, thank you, that's brilliant. So just one question, you can ignore the second question, it's not been filled in. So yeah, oh good, I can see a few people putting in some information now. So we'll give you time for everyone to have their say. So it's just the one question for this poll. Give it a couple more seconds. Yep. A few more. Okay, so shall we end the poll now and just share the results? So I hope everyone can see the results there. So fairly balanced mixture of you. I think quite a few people at the beginning of your retrofit journey are knowing a little bit, and then a few others actually quite knowledgeable. So we've got quite a spread of knowledge within the audience here today. Okay, that's brilliant. That's the end of the first poll. And close that down. Right. So the only other thing I was going to mention is that we have a brand new Facebook group for Green New Build and Retrofit. So again, I'll send that out in the email at the end after the webinar, perhaps tomorrow. But that's something to look out for if you're interested. So over to our presentation. So Marion Lloyd Jones of People Powered Retrofit and is going to be talking to us today. She's the service design lead at Carbon Co-op, and she has responsibility for developing the systems and the processes. And she's also a retrofit assessor. I think, Marion, perhaps you can say a little bit more about what you do, but Marion's done a lot of different things all within construction and sustainability. So.
Hello, thank you, Tina. Yes, I've been with Carbon Co-op for coming up 3 years now, so a year on People Powered Retrofit. And before joining Carbon Co-op, I was a sustainability consultant for 5 years. So I've seen sort of the corporate side of things and realised I'd actually rather work for real people, improving their homes, so taking more direct action on climate change. So let's get sharing with sound.
Okay.
Here we go. Can you see my screen? Are we there? Brilliant. Okay. So these are the things we're going to go through this evening. We're going to talk about the whole house approach to retrofit. And then we're going to break down the various systems in our homes into heat and air, moisture, and then we'll wrap up and do a Q&A at the end. So let's go. I think Tina's introduced me. And I'll take a moment to introduce people-powered retrofit. So people-powered retrofit started out as a funded supply chain pilot from BEIS, who the Department for Business, Enterprise and Industrial Strategy, I think. It's the bit that used to be DEC, Energy and Climate Change. It's that bit of government. And we are essentially a one-stop shop for retrofit. So that includes an end-to-end service for self-funding householders. So we'll take people all the way from advice at the very beginning. Can I do retrofit? Am I in your area? We'll take them through an assessment, design, on-site, and then handover. So we will hold a householder's hand all the way through that journey. We also do work with the supply chain, a bit that's very much missing. So we do training with the supply chain, and we also help network contractors. And we have a software arm that deals with various things, including our home retrofit planner assessment tool. So we operate as a service in Greater Manchester and slightly outside that boundary as well, but because we're focusing on a local supply chain, we're very much trying to keep it within Greater Manchester. And there is some replication of people-powered retrofit. At the moment, it's limited to the Home Retrofit Planner Assessment Service, which CAFs use. It's also used by the Centre for Sustainable Energy down in Bristol and Devon Council. And we've got another couple of organisations looking to use it as well. So let's start with a whole house approach. So we're going to talk about what is a whole house approach and why is it important. Talk about what fabric first means, and we'll have a little talk about some different housing types as well. So the whole house approach is based on the premise that a house is a system with lots of different elements to it. So that'll include heat loss through the fabric being the walls, the floors, the roof, the windows, the physical constructed bit of the building. Ventilation, so that's both planned ventilation, like your extract fans, but also unplanned ventilation, so that's drafts and that kind of thing. Heating, most houses now have a heating system put in, so this is inside the house. And we've got lighting and appliances. We'll see what effects they have on the house system. And people, you can't forget people in this situation. The way the very act of living in a home changes the energy flows within it, and how those people interact with any systems that you install. And what's really important is the way that all these systems interact. Sometimes it takes place in ways that are easy to understand. If a person gets too warm, they're likely to open a window. But sometimes it's hard to predict in a specific circumstance. So we use a whole house approach because, you know, houses are complex systems. There's lots of variables and the context can be very complex. So we take a very context specific and a risk management based approach, which means that we're aware of the potential for unintended consequences. Knowing that risks increase the bigger the change proposed to the existing context. So risks associated with very high levels of insulation and airtightness have a bigger chance of creating damaging unintended consequences if the context isn't well considered and the measures are not well designed and well installed. There is a great tool from the STBA, which I can never remember exactly what they are. Tina, can you help me out? It's gone from my brain. Oh, the Sustainable Traditional Buildings Alliance. There we go. They have this fantastic, oh, this fantastic tool on their website. If someone can pop the link in the chat, that would be great. So this is on their website, and what it does is it allows you to understand what the potential interactions are between different retrofit measures that you might install. So you can see that on this wheel, it's been selected ventilation, and we can see that there are interactions here between many different parts of the building. If you can know about a risk and understand it, then you can know what to do to mitigate it. But it's not as simple as just deciding that you want to get from here to there. You need to make a plan, and this is where a whole house approach can really help. It doesn't mean that you have to do everything at once. I'm not saying that everyone should spend, 30 grand on a retrofit straight off the bat. But it is important to make a plan and understand how any measures that you might want to install will interact with each other. Basically, what we're saying here is, we don't want you to spend money on getting something installed in your house, and then when you want to do the next thing, you have to undo part of what you did the first time round. With good planning and preparation, you can minimize this and make sure that, for example, if you install underfloor insulation, you can already prepare the interface between the floor insulation and any wall insulation, for example. If you know that that's part of the plan, you can prepare for that. So, fabric first. What do we mean by fabric first? So the rationale first is that we've looked at lots of post-completion monitoring, and there's very often a performance gap between the intentions and the outcomes. So you can model a retrofit and say, well, I think if we install these measures, this is going to be the outcome on energy use or heating demand or something like that. But very often there is a gap between what was modelled and what actually happens in real life. So we take a fabric first approach to try and reduce that performance gap. So we work with this energy hierarchy. The first thing to do is to reduce the space heating demand. If you can reduce the amount of energy that needs to go into a home, well, you're already doing a brilliant thing for your carbon footprint there, let alone your bank balance. And this means sort of fabric energy efficiency, so improving the fabric of your home. Common things for this would be insulation, airtightness, triple glazed windows, that kind of thing. Then, once you've reduced your energy demand, we want to use that remaining energy efficiently. So we want efficient heating, efficient lighting, and efficient ventilation. And finally, we want to get the supply of that energy from renewable sources. Now that might mean some solar panels on site, but there are other options in there. But we would always put that at the end of the hierarchy, reduce demand first. So why do we take this approach? Well, it has lots of co-benefits. So insulation makes you warmer, as well as reducing energy. It also makes it easier to make more stretching targets. If you've already reduced your energy demand, then your building services, your heating, it needs to do less work. So you can have a smaller sized heating system, which can be more efficient. There's often lower maintenance through the building's life as well. As when you do retrofit, you should do the maintenance work first. We don't want you building in problems. You can have reduced ongoing running costs, you're using less energy. Better living conditions and well-being. We can really help to improve indoor air quality in the indoor environment through well-designed, well-thought-out retrofit. I've got on it hasn't made it onto the slide, but it's been put in the notes to avoid eco-bling. So this is where you can have a house that is a terrible performance energy efficiency wise, but you could theoretically stick loads of solar panels on the roof. You'd get your lower EPC and you'd be generating low carbon electricity, but you're still using a lot of energy to run that house. Through fabric first approach, we can reduce fuel poverty. If you're keeping that heat inside the home, you're not needing to top it up all the time. It future-proofs your home for changes of temperature, and we're not just talking about things getting colder, we're also talking about the climate getting warmer. I'll come to that later. And it's an easier approach to to achieve target CO2 savings. So it comes back to this reducing the demand. It's easier to reduce demand than it is to rely on technology to reduce the carbon intensity down the line. Okay, so this is one of the challenges that we come across in retrofit. This slide shows, it segments all the houses in England, this is, by age. And you'll see this a lot when talking about retrofit. The main reason for this is that the way we construct buildings has changed significantly over time. There's a large spread here. You can see a lot of housing was built pre-war, and then there was another boom post-war, and then after that we haven't really been building houses very much. Certainly nowhere near how we were in the 40s. And what's really important here is that buildings, houses from pre-1919 make up about a fifth of the total housing stock, and the construction methods for those pre-1919 houses are very different from what would be built now. So it's really important to understand the context of the age of your building when you start looking at your whole house plan, to make sure that you understand what is there, how was that building originally designed, and how is the way that we live in it different now. I love these diagrams. Okay, so the way that buildings have changed, sort of traditional buildings, your older buildings, they were designed around point source heating. So you'd have an open fire in many rooms. You didn't expect to be warm unless you were right next to that fire. There were lots of losses through the fabric of the house. But there were also lots of exchanges within those walls. So moisture could find its way in, but it could also find its way out, because those materials that the houses were built from were more breathable. I'll come on to this later. Breathable is not about air, it's about moisture, but I will detail that more in a moment. Modern homes, by contrast, we have here, we've put a lot of extra stuff in our houses since they were built. We've added central heating to most houses, double glazing, and we've draft proofed to make it more comfortable. But this has fundamentally changed the flows of energy and moisture in those buildings. Okay, have a little break, let you guys have a little think now. So I'm going to do a couple of these this evening, knowledge checks. What I'm going to do is I'm going to ask you a question, and if you can type your answers in the chat, but don't press send until I say so, we'll let everybody have a go. So, first question. What does it mean to take a whole house approach? So type your answers in the chat box, and I'll give you a few moments, and then we'll say go. I've realized actually in this view, I can't see the chats over here. Okay, and go. Press enter if you've put a something in there. Oh, look at this. There's people there listening. This is fantastic. Looking at the whole house, how everything interlinks, house system. Brilliant, you've got this. Okay, I will move on. Think about all the issues involved, absolutely. So we'll start with heat. This is the one that we're thinking about the most at the moment. So one of the main goals of retrofit is often to reduce the heat loss. So these diagrams are from our home retrofit planner assessments, where we model 3 different scenarios for a given home, which are usually cumulative. So you do scenario 1, then you do scenario 2, and then 3. And you can see here that these numbers around the outside are showing your losses, and these are both fabric losses, and it also includes ventilation and infiltration losses on this diagram. So you've got planned ventilation down the bottom, and it labels them as drafts up the top, but this is unintended ventilation here. And you can see that as we go through the scenarios, we've reduced the heat loss from these various different elements, and we can get down. So this started off with 500 watts per Kelvin loss down to 159. So that's a big reduction you can do there through the fabric. But heat loss is only half the story. there are many ways that we generate heat inside our homes. So again, this graph here shows is again from the home retrofit planner, and it shows the baseline, so what the home's like now, and then how things change over the scenarios. The key thing here is we see this 0 line. Anything above the line, that's a gain, so that's heat coming into the house, and anything under the line is a loss, so heat leaving the home. And you can see here the big orange block, that's your fabric losses, and you see that we've reduced that a lot as we've gone up through the scenarios. This sort of tealy bit here, that's your ventilation and infiltration losses, and these gains come from internal gains, which can be things like cooking, your electrical appliances, but it also comes from the people. So each person creates about 100 watts of heat. When sitting down, you create more heat when you're more active. You've also got in here solar gains, so that's pure heat from the sun coming through your windows and warming up your home. And this orange block up at the top, that's your space heating requirement. So that's the heat you need to add using a heating system, so that it balances out these losses. So we'll talk about ventilation and infiltration in a bit, but as you can see, especially once you've reduced the fabric losses, that these ventilation and infiltration losses can become quite significant as a proportion of that residual heat loss. Space heating demand. Okay, so this is what we think is quite a good metric for measuring and comparing homes and scenarios. So this is so the unit for this is kilowatt hours per meter squared per annum. So that is how much energy per square meter of your building, how much heating do you need per year, and it's by meter squared, so that you can average it out. It's more comparable from home to home. All homes are different sizes, but this metric really strips out that size, the size factor in there. And you can see that things are, it's pretty variable. The UK average is about 140. Building regs since 2000 was down to about 100, and that's improved down to 65. AECB retrofit standards 50, and if you look all the way down the bottom, a passive house is 15. So you can see there's a massive difference there between the average of 140 and a passive house, which is 15, and Enefit on there, which is 20 to 30. That's the passive house for retrofits. So passive house is for new builds, Enefit is the retrofit version. So you can see we've got a big variation there. One of the things that can really make a difference, but unfortunately can't do much to change, is what we call the form factor of a building. So this is a ratio between essentially the area of exposed fabric and the floor area. So you can see that a mid-floor flat has a very small form factor. It doesn't have much, comparatively, not much outside wall compared to the floor space, and the form factor gets bigger as you go down the list. So bungalows are the least efficient. They have an awful lot of surface area to lose heat from. So if you're buying a house, I would recommend trying to find one with a good form factor, but we're in a housing crisis at the moment, so it's not always one of the things that'll be high up on your list, but it can make a massive difference to space heating demand. Another metric you might hear talked about is peak heating demand. So this is in watts per Kelvin, Kelvin being 1 degree Kelvin is the same as 1 degree Celsius. And this is what you need at your peak. So on the coldest, cloudiest day, what is that peak demand, which is an important number for sizing heating systems. When you're sizing a heating system, you need to know that it's going to keep you warm on the coldest day. You can also, there's also something to consider here around the impact on individual houses and on the grid on a cold winter day. So we want to keep that as low as possible through fabric improvements. and what's possible in retrofit. I think this graph's really interesting. So this is showing, it's again space heating demand, and this is looking at 5 different houses. The blue bars are before the retrofit and the red and yellow bars are after the retrofit. And you can see here there can be a real difference between what was modelled and what happened in reality. There can be various reasons for that. Occupant behaviour being one of the biggest ones, but we're trying through sort of across the sector to really reduce that difference between what is modelled and what actually happens. So it's not unusual for buildings to use up to twice as much energy as predicted on the Energy Performance Certificate, the EPC. I'm not going to go into why that might be in too much detail, but I will be speaking on a panel at Future Build about why the methodology for EPCs isn't brilliant. But we can mitigate this difference through making appropriate assumptions at the design stage and when we're doing modelling, using something that is more close to what we know to be reality than some numbers picked out the air. Attention to detail in the design. It's all very well and good having you know, great insulation on your home, but if where that insulation meets like turns around a corner or meets a different floor, meets another element, the floor, the roof, if the junction between those elements isn't well detailed, then it's not going to perform as you modelled it. We need quality control during construction. We've spent time putting time and effort into a good design. We need to make sure that what we've designed is actually what's happening on site. We need suitable commissioning and handover. Again, you know, you can have the best heat pump in the world, but if the person who lives in the home doesn't know how to use it, it won't run efficiently. It won't be great to live in, and you won't get, again, it's another reason why you'll have a performance gap. And also appropriate maintenance when it's in use. Some say internal wall insulation, for example, if you're not aware of how to maintain it, how to treat it, then you can reduce its effectiveness, for example, by puncturing membranes and things. So people need to understand what has been installed and how to use it. And again, this is another graph just really highlighting that. Oh, my labels have come off. But basically from left to right, this is showing, again, that UK average, buildings regs, sorry, old building regs, newer building regs, and then the ACB standard. The bar would be what was modelled. The error bars would be the range you could expect to see afterwards. What's really important about this is you still get this degree of variation for passive houses, for example, across the country, but it doesn't matter so much, because for passive house, 30% of nearly nothing is nearly nothing. So it's less of a problem. But when you have a large variation range on a home that's already using a lot of energy, you can see it can really make a difference to the numbers. So we've got another knowledge check. Remember, type your answer, I'll say when to hit enter. So what does space heating demand mean? Give you a min, have a bit of tea.
Marianne, while everyone's thinking about that, you might check the Q&A questions. I think there's one about, which I think was when the form factor question came in about.
Yes. So
afterwards, or
yeah. I'll just put I'm assuming the question about, is this based on internal floor area? The form factor is yes, it's the treated floor area, which has a specific meaning. But yeah, it's about floor area versus exposed fabric. So I'll say I've answered that one.
I think your answers are coming in.
Marvelous. Let's go. Hit enter. What we got? Yes. Amount of heat required. Yes. How much energy to heat a home? Heating to make you feel comfortable. That's a really good response. I like that we've focused on comfort here. Excellent. All right. So we're going to move on to comfort a little bit. So there are heating targets, and I think this is very important. Recommended minimum internal temperature would be 18. Generally, we tend to model for 20 degrees as an internal temperature after retrofit. Below 18, you start to get other issues, not just that it's a bit cold, but I think there becomes an issue with potentially with humidity once the temperature goes lower. I'm not going to go into relative humidity too much in this this session, but it is an important thing to understand with retrofit, the relationship between temperature and humidity. Very briefly, relative humidity will increase as the temperature goes down. There's an inverse relationship there. Okay, so heating targets. We talk about all this about heating, but what should we heat to? Thermal comfort is an academic subject which has I get really excited about, and so do lots of academics. But what we're talking about here is how you perceive a comfortable temperature. And the way we perceive warmth is affected by lots of different things. Air temperature, that's usually what we're measuring, that plays a part, but relative humidity plays a part, air velocity, so that's sort of wind speed, and radiated heat from other objects. So these two scenarios on here, the temperature is 22 and the relative humidity is the same, but the air velocity and the radiated heat from that wall are very different in these two circumstances. So we will feel differently in those two locations, even though the air temperature is the same. Okay, so we're going to talk a bit about some heat transfer mechanisms. I'm going to concentrate on two specifically for this section. Conduction, that's the heat moving through a material, and radiative heat or radiation, that's heat being released from a material. When we talk about temperature, as I say, we're usually talking about air temperature. However, we perceive both the air temperature and the radiant temperature of surfaces around us. So everything that's above absolute zero, which is minus 273 degrees Celsius, so pretty cold, everything above absolute zero is radiating heat, even if it's a very small amount. And you can measure that heat with some quite simple tools. This is an image from a thermal imaging camera, and you can see that all of these surfaces are radiating some kind of heat. Some of them are not radiating very much heat, but there is heat coming from all of these surfaces. And the way that affects our comfort is that we actually feel cold surfaces much more keenly than cold air. And if there's a big difference between surface temperatures around us and the air temperature, then we will feel uncomfortable. Generally, a difference of about 4 degrees or greater will start to be felt. And I'm sure a lot of you can, I'm sure that this will resonate with a lot of you. If you're sitting in a nice warm room, heated at 21 degrees, if you're sitting next to double glazing or single glazing, you will feel the cold from that window quite keenly. If that window is triple glazed, there will be less of a difference there between the surface temperature of that window inside and the room. So it's a really good example there. I know that I definitely notice if I'm sitting next to a window that hasn't been properly draft stripped, or if the vacuum's gone in the between the panes. So how do we improve comfort? So for this one, you can pop your answers directly in the chat. If you wanted to help, if you're uncomfortable in your home, what do you think you could do? So anything you can think of, do pop your answers in there. You know, how can we address this issue? What makes you? How can you feel more comfortable? Awesome. Draft proofing, yes. Curtains, yes. That's that surface temperature thing. Drafts are definitely a thing. Reduce the heat loss. Insulation, I like this one. Wear thermals, move about, blankets, closed doors. That's what I do in the day, so I won't put my heating on. Heat comfortably spread out and not just in one place. Yeah. Hot water bottles, very very apt. Super. So, you know, you've come across a lot of the things we would suggest you do. So addressing the cold, let's start with the cold. That's what we're all bothered about this February. Insulation. Insulation does two things to help you keeping warm. One, it reduces the conduction of heat through the walls, so it slows that heat loss through the fabric and keeps that heat inside the house. But it also raises the surface temperature, particularly external wall insulation. You can go from having a very cold external wall to having a wall where that temperature differential between the air and the surface is not too different. And that, as we've said, that can really help with your perception of warmth. It doesn't affect the radiation and convection heat pathways to the same degree. It's mostly about preventing conduction, but that difference in surface temperature can really is really noticeable. We've got some examples here of some insulation. So still air is a really good insulator. And most types of insulation are simply different mechanisms for trapping small pockets of air within a matrix of another material. These are examples here of wood fibre insulation. We've got some internal wall insulation here, wood fibre, and this is external wall insulation with wood fibre. And this one in here, I don't think is wood fibre. That looks more like a mineral wool or something, but you can get fluffy wood fibre insulation as well. Other insulations, sort of you're not more, say, less eco insulations, tend to use different gases inside the pockets that are even better insulators than just still air. But there are various issues with these kinds of insulation, one of which being we don't really know how long those gases stay inside the insulation and where they might go when they come out, which means their performance may vary over time. The best insulator you can get is a vacuum. Think of your thermos flask, but a vacuum can be very difficult to maintain and isn't very practical. If you want to learn more about insulation and insulation materials, etc., including how to measure their effectiveness, U values, and so on, then that will be covered in Unit 3 of this webinar series. So we've talked about cold. We also need to address heat. We need to keep cool when it's hot, something that we're seeing more and more of. There are varying ways we can approach this. One of them is not having too much glazing, but we like a big window, let's be honest. It's nice to be able to see outside, and daylight is a wonderful thing. But we can think about how we position those windows sometimes. We can add shading. That can make a real difference to the solar gains through windows. And it doesn't have to be sort of complete shading, shutters. There are various, we can do it through vegetation and lots of lovely architectural ways of adding shading. We can think about the materials. So it says here decrement delay. What that means, that's talking about the speed at which heat moves through a material. So some of the denser insulation materials, the heat really does move quite slowly through those, so you can really maintain the heat. And ensuring ventilation. We really want good indoor air quality, which means getting rid of that stuffy air in the summer. I would say a particular thing to think about in addressing heat is attic rooms or rooms in roof. Some of those done with some of the more common forms of insulation, your like PIR foam boards, your Celotex, your Kingspan. Those loft conversions can get so hot in the summertime because the decrement delay on those insulants is not great. You can sometimes buffer that by using sort of a more dense insulation material. So move on to heat and air. So now we're going to bring ventilation and infiltration into this. So the main mechanism we're talking about here is convection. So this is how hot air rises, warm air cools, and you end up with these currents of moving air. So if you think about convection, this can sort of manifest in several ways. One of them is, so we're going to go through these in more detail. I'm just going to list the mechanisms I'm going to cover. So we're going to think about thermal bypass, the chimney effects or stack effect, infiltration and drafts, and ventilation. So thermal bypass is essentially about getting warm air on the wrong side of your ventilation, or conversely cold air on the wrong side of your ventilation. You will have some air movement inside your insulation, which you will get forming these currents. You do want a bit of ventilation over the surface, probably, to help deal with moisture. What you don't want is air rotating from the cold side to the warm side through gaps in insulation. Thermal bypass can actually reduce the effectiveness of insulation by around 30%. So this is a key thing. A classic example of thermal bypass that you see a lot of is air movement behind dot and dab plasterboard. So you can end up with cold air circulating behind the plasterboard, which cools down the surface of that wall, which makes it feel colder, which we absolutely do not want. The chimney effect. Now, this is a useful thing when it's in an actual chimney, but what we don't want is your entire house acting as a chimney. So this example here is in an uncapped party wall. So in here, you've got cold air coming up the cavity, being heated up by conduction from the occupied space. And then the warm air then escapes the cavity into your loft, which is supposed to be a cold space, which can cause all kinds of problems. We can also have an issue with convection in here, in the same way that you get this air movement up and down the cavity. There are ways you can tackle this. So we can cap and fill chimneys, which can be a big job if you've not already got scaffolding up, but definitely capping them will help. We would definitely recommend you fill cavity walls where possible before adding external wall insulation, so that you don't have thermal bypass in the cavity. And you can fill or cap cavity party walls as well, just to really stop this heat movement. We want to keep the heat on the inside where we're living. We don't want to be heating up other spaces. Right. So this is really important. There is a big difference between infiltration and ventilation. So infiltration is unplanned air movement through the structure, typically felt as drafts, contributes to heat loss and potentially increases moisture within the structure. So this is, I always class infiltration as unwanted ventilation, and ventilation is the planned exchange of air within living spaces. So this is about delivering fresh air to the rooms where you need it, and removing stale or damp air or polluted air from the spaces where those are generated. Now, we especially want this in sort of wet rooms like kitchens and bathrooms, but there can be other reasons where you might want to increase ventilation as well. So very important. Infiltration, unplanned. Ventilation, planned. We want to reduce the infiltration and make sure we have sufficient ventilation. Very important. So this is exploring where infiltration happens, and it's really important to understand this, because infiltration can be responsible for up to 50% of heat loss in an otherwise insulated home, you can put so much insulation on your home, but if you've got lots of unplanned ventilation, then you're not really taking advantage of all the good work that insulation is doing. And you can see here there's lots of mechanisms for drafts. We've got drafts going through stairs and through floors and around windows, up the chimney. But with high levels of air tightness, we've only got air moving through the places we've planned for air to go. So we've got an extract fan in this bathroom, and we've got inlets and extract bedrooms. So we can measure the leakiness of a building. We talk about air permeability, so that's leakiness essentially. We do this with a pressure test. So someone will come along to your home and they'll do what's called a blower door test, which is kind of what it sounds like. You put a big blowy fan in your door usually, and you either suck the air out to depressurize the house, or you blow air in to pressurize the house. We're not reducing when you depressurize a house, you can still be inside it. You're not depressurizing it to a point where you're sucking all the air out and you can't be in there. But what we're doing there is we take it down to a known pressure, 50 pascals, and then we can measure that. Now, annoyingly, there are two different ways of measuring this. One of them is air permeability, which is what's in the buildings regs. This is about the volume of air compared to the surface area of the building. And the other way of measuring it, like down the bottom, is air changes per hour. This is about the volume of air leaving compared to the volume of the building. So this is when we talk about air changes per hour, we're talking about how many times in an hour does the entire volume of air in that building get exchanged. I'm not going to dwell into this too much, but just so you're aware that these are terms that you might come across when talking about air tightness. So we can improve the air tightness of our homes. This will reduce heat loss and make the home more energy efficient. It'll also make it more comfortable. If you can reduce drafts, especially around ankles, the back of your neck, these places where we feel drafts most keenly, then you can really improve comfort levels. So by insulating, minimizing thermal bridges, checking where your air movement is, keeping an eye out for thermal bypass, chimney effects and drafts, should make your home a lot warmer. Unit 2 of this webinar series is about air tightness, which will go into this in much more detail. So we're going to do another knowledge check here. Fingers at the ready. So what is the difference between infiltration and ventilation? Get your answers ready. And then go. Hit your, yeah. Okay, infiltration bad, ventilation good, correct. Excellent, we've got this. I was having a quick squiz through the Q&A. Oh, there's some good ones. Oh yeah, right, yeah, we'll definitely come to these. Fantastic. Right, you've got this. Be able to go to the next webinar and you'll already know. So we'll move on to moisture. Now, it's the last one that we're going to cover, but it is actually really important. Moisture and ventilation are covered in more depth in Unit 4 of this series. So if we come back to this, this image again, if we think about heat without considering moisture when we do a retrofit, then we are certainly going to lead to problems. As well as being heat flows around our homes, there's also moisture flows, both in the air, so water vapor, but also in the building materials, because as heat moves through materials, moisture also moves through materials, although depending on the material, it depends on how moisture will move through it. But the important thing is that these flows are very much affected by heat. There is a real relationship there between heat and moisture, and controlling moisture in your home is really important to protect both your health and the fabric of the building. So I am going to attempt to put a video on. Oh, let's see if I can do it. Not this one. Ah, I've lost it. I can't move this bar. Oh, yes, I can. There we go. Okay, this is a short video, but it really explains moisture in buildings very well.
Worried about damp and mould? Don't panic. Help is at hand. First off, we need to understand what the problem is. Damp and mould are caused by an excess of moisture and can create problems for our health and for our buildings. However, just like our bodies, we need some moisture in our houses in order for them to function well. So we need a balanced amount of moisture to keep a healthy home. Moisture can create problems in your home through the many forms water can take. When water freezes, it expands into solid ice, which can burst uninsulated pipework. Liquid water from leaks or flooding can lead to damp in the floors or walls. If your guttering becomes blocked, then rainwater can overflow, saturating your walls in specific areas, sometimes even leaking through to the inside. But the most important form we want to discuss here is water as a gas, water vapour. Whilst we're all used to the sight of steam from a boiling kettle, most water vapour is not so easy to spot. There is always water vapour in the air around us. We produce it when we breathe, along with any animals or plants in our home, and also through daily activities such as cooking and washing. If there was no water vapour in the air, then nothing would be able to live. Okay, so here's the technical bit. At different temperatures, air can hold different amounts of water vapour. The warmer the air is, the more moisture it can hold, known as its holding capacity. But when there is more water vapour than can be held by the air, it becomes full up and condenses into liquid water. Outside of your home, this is how rain is formed. This also happens when warm, moisture-rich air meets a cold surface, like a single glazed window in your home during winter. Condensation forms as the air suddenly cools against the surface and the holding capacity of the air is reduced. Because air can hold different amounts of moisture at different temperatures, we measure how full the air is by something called relative humidity. If we have 100% relative humidity, then the air is full up and the vapour becomes liquid water. But even when there is no condensation, high relative humidity can be uncomfortable and lead to mould and other problems. At the other end of the scale, air with 0% relative humidity is excessively, and in fact, impossibly dry and uninhabitable. We need a relative humidity of somewhere between 40% and 65% for most of the time for the building atmosphere to be pleasant and healthy. So we come back to balance. Not too dry and not too moist. Where does the moisture in your house come from? Outside of the home, the most obvious answer is rain. Good construction is vital to avoid water entering a building from the roof, walls and windows, along with suitable ground drainage in the case of flooding. Inside, we have our direct uses of water in our daily lives, washing and drying clothes, cooking and bathing. All these produce visible liquid water and large amounts of not so visible water vapour. Next, we have the organisms within the home. Human, animal and plant. All of us produce water vapour as we breathe, or plant breathe. If the number of people, pets or plants changes, the balance of moisture within your home may change dramatically. Remember how hot and humid the air gets at busy parties. But you didn't have a problem before. What's changed? For damp and mould to appear in your home, you need an excess of moisture, visible or not, that leads to an imbalance.
Okay, I'm going to pause it there and come back to the presentation. I will when you get the slides, there will be a link for this. It's just a fantastic video that really explains where moisture comes from and what can we do about it. So do have a look. Okay, I've now got a thing in my way. Okay, so we'll talk about the issues here. So if water vapor continually condenses on surfaces or within a wall or a roof or a floor, it can damage the materials and cause rot and decay. And I'm sure this is a site that unfortunately most of us are probably quite used to. Lots and lots of black mold on walls. This is mostly caused by condensation. It's difficult to reduce the amount of water vapor in your home. You're producing litres of it just by breathing. Sorry, just a moment. Had a visitor. So there's this quote gets used an awful lot in retrofit, but it's very, very true. A retrofit project that does not consider ventilation is a condensation project. What you do when you add insulation to a wall is it changes the dynamics, the heat flow and the moisture flow dynamics in that wall. This first wall on the left is your standard 215 mil Victorian brick walls. It's a normal solid brick wall. And you can see here that you've got good flow. So you've got, you got moisture coming up from the ground. That's capillary action. We can't do much about that. And we've got heat inside, and we've got some moisture coming out through this wall. But if we stick some impermeable insulation on the outside of this wall, well, the moisture can't come out like it used to. And you end up with a buildup of moisture within that wall. There are ways around this. By using this calls it a breathing insulation system. I like that. You might call it breathable or vapor permeable. And these kinds of insulation allow that moisture to still work its way out of the wall, which is absolutely what you want. Draft proofing and improved air tightness, they change the air movement patterns, which affects the moisture patterns. Really important here, breathability. Not about air, it's about moisture. Construction can be airtight and breathable. So it's a little bit confusing, but breathability is about, essentially it's water vapor permeable, which means water vapor can move through the construction. It covers several things, including this vapor permeability, but also hygroscopicity. That is about how a material buffers moisture, and also capillarity. That's about how moisture can be sucked up a wall, essentially. And we're nearly there. So ventilation, it's the last thing, but it's also the most important thing. A whole house retrofit project must always have a ventilation strategy. We will always need a supply of fresh air, and we will always need to extract wet or polluted air. Now, there are various ways of doing this. You may have single point extracts in your wet rooms and inlets in your living rooms. You may have a centralized extract point. And you might have some heat recovery from your extract air as well. There's many different ways of achieving good ventilation. Again, I refer you to Unit 4 of this course. So let's wrap up. Key things. So the house is a complex system. We've got heat loss through the fabric. We've got ventilation. We've got heating systems. We've got lighting and appliances, and people, who are the most unpredictable part of the system. All of these systems interact, but mostly in a known way. So we can approach, we can have an approach to how we deal with all these things. Oh, and I made it 3 minutes over, Tina. Done all right. Ready for questions.
Brilliant. Thank you very much, Marion. That's great. So next steps, if you haven't already done so, do sign up to our CAFS newsletter, because that way you always get told every month if we've got webinars happening or any other events or anything that might be of use to you, like this free webinar series that we've got going at the moment. I hope to see you at another webinar. By all means, complete our survey, which I'll be sending out in a follow-up email at some point later this week, to all of you and anyone who booked on but couldn't attend today. So we'll provide information on ways to get in touch with us and what else you can do to follow up. Again, a big thank you for all your donations, those of you who donated when you booked on, and hope to see you again very soon. So thank you, everyone. And if you've got any last comments, or you want to pick up Marion's email address, then please do. I'll leave it open for a few minutes afterwards. But that's it. Thanks again to Marion. It's been really great to have such a wonderful presentation to kick off our Eco-Retrofit for Householders series, and hope to see you all again very soon.